So last time what we talked about was in the main lecture was the Hebbian, a simple Hebbian network. And so let's just kind of review that. So okay, so we had a Hebbian network, and it had no interconnections. So the weights were changing. So the weights were changing, but we only had feed forward, so there was no feedback connections. And we also had no interconnections in layer either. Within the layer. Of course, in real life, we have a lot of connections, like we have the cortex, it's all connected to its neighbors. So, does that mean that you can't do a Hebbian learning network with feed-forward connections? No, this was just our attempt to ridiculously oversimplify things so we could understand them. So we just started off with a Hebbian learning network with no feedback, no connections, no interconnections, no feedback from higher layers, but we're changing the weights. So what we're going to talk about today is an attractor network. And we'll explain, why it's called an attractor network. And now we're going to fix the weights. Now, this isn't the only kind of attractor network. It's possible to do an attractor network with Hebbian learning in it. We're not going to do that just in order to understand what's going on. So we have fixed weights, and we're going to connect everybody up to everybody else. So fully interconnected. That's the most you could possibly get. Now, stressing again, we don't mean to say that there's all different kinds of combinations of networks. We could use Hodgkin-Huxley neurons, do some weight change, have some fully interconnected. We could do all different combinations. But what we're going to do is just look at the dynamical behavior. So in this case, we were looking at the dynamical behavior of the weights, like how do the weights change. Here we're going to look at the dynamical behavior of the activations. And we're not going to change the weights. And just see how the networks evolve over time with their weights the same. So what is the relevance of the fully interconnected? Well, in the Hebbian learning network, we basically just had a situation where a unit over here went to some units up at the top. And what we would do is we would apply an input, calculate the output, and then we're done. But if we have a situation where units are hooked up to each other, then you've got a more complicated situation, because what happens is you're in some state, and then you see what the inputs are, and then you update yourself. But update yourself means you might affect somebody else. And so then you're not done yet. You have to keep updating in order to figure out what happens to the activity, as opposed to this one. We just do one update, and then we're done in terms of the activation of the second layer. So what we're trying to do is to try to understand what's the typical kind of behavior that you get in these networks when they're fully interconnected. And one of the things that this has been used to try to model is categorization. And so what do we mean by that? Well, if you've got a whole bunch of examples of something, like the example I always use, which always brings up my most famous error on an exam, here's a bunch of dogs. And so one of the things we want to do when we categorize dogs is just sort of come up with the typical dog, or just recognize that's a dog. I don't care exactly what kind of a dog it is, I just know it's a dog. And you can sort of think of this as, in a way, as losing information, because these dogs are all specific, Saint Bernard, Chihuahua, you've got all these different dogs here, but then when you look at one of those dogs, somewhere in your brain, something says, oh, that's just, that falls into the category dog. So this is the dog category. And similarly, there might be something that is, not a dog, say like rodents or something. So there's going to be another category of things. Anything that sort of looks more or less like a rat or a mouse or a hamster, goes into this other, another category. And so the thing that somebody said, so I asked a question on one of the exams, what have attractor networks been used to model? And I wanted something like, well, categorization is an example. And so way back in the when, I was talking too fast. And so I said, Chihuahua is not a canonical dog. So that was like a double negative. It used a word, sort of an unusual word, canonical, church canon. It sort of means typical. So what I should have said was a Chihuahua is not a typical dog. It's a little smaller than a typical dog. And so the great answer I got on the test is, the question was, what do you use attractor networks to model? And so somebody said, this is the answer, Chihuahua is a conical dog. Conical dog. And then they kind of knew that wasn't quite right. But just to indicate that they actually meant conical, they drew a little conical Chihuahua like this at a tail. And so if they had only said a Chihuahua is not a canonical dog, not a conical dog, I would have given them half credit. But so that was the conical dog. So canonical dog. So what are attractor networks for? One thing that could be for is categorizing things, but another thing that could be for that could be used for is pattern completion. So imagine you've got like a bunch of A's, but some of these A's are occluded. So maybe this guy's got a little sort of spot over here, or the typewriter didn't work too well, or there's maybe that guy's sort of degraded in some way. So those images are quite different from each other in terms of pixels. But what we would like to do is, one thing we'd like to do is just reconstruct an A, fill in, sort of complete the pattern, the parts of the pattern that are missing, and get an A. So that's another thing you could use attractor networks for. So let's just quickly start off and say, why are they called attractors? So if we consider, again, we've only got 2 dimensions to work with, so let's just consider what we call the activation space. Activation space, or a lot of times this is called the state space. So what does that mean? Well, that means here's unit 1, and here's like 0 to 1. Say that one just goes 0 to 1. And here's unit 2. And here's 0 to 1 there. So why do we call these networks attractors? We call them attractors because if you say this is an attractor here, 0.9, 0.9, and 0.9. So say that's an attractor. And then say we got another attractor here at 0.1 and 0.1. So why is it an attractor? It's an attractor because if we start off the network in this state, so what is that state? So that state is 0.6, 0.6, and 0.9. And then update the network, it goes to that state. But it turns out, if we start the network off over here, it also goes to that state, or over here it goes to that state. So basically it kind of attracts the state of the network, or even over here, it goes to that state. But then if we just slightly go over the boundary over here, over the boundary, and so say the boundary is down the diagonal, so slightly over the boundary to over here, instead of going to that guy, we'll go to this guy. And so basically what an attractor network is it kind of goes to a particular stable state. So we have to sort of define what that is, but let's just put this here. So this guy is a stable state. And what is stable state? That just means a state that's not moving in the activation space, meaning that it doesn't mean that the neuron isn't active. So this guy will be active 0.9 and that will be active 0.9. It just means that it's not changing over time. And so here's another stable state. And then this guy is an unstable state. And what is unstable state? It just means some state that if you update the network, it doesn't stay. It changes. So that's basically the idea of an attractor network. Now, is this a very good model for the brain? This is what I always say. Absolutely not. Like if I look at a dog, in some respects, these networks are very boring. You start them off in something, and then they just go there and just stay there. So does that ever happen in real life? I look at the dog, and I just go, dog, and I just get stuck in dog. Clearly, that doesn't happen. Like I look at the dog, and then I say, oh, it's a dog. Okay, then I do something else. So this is kind of we always have to start simple. So it's just a way of looking at what are the typical kinds of patterns that you can quite easily get out of a network of interconnected neurons. And attractors are one of them. So let's start off with giving an example of one of these networks. And in order to sort of have a simple example, we need some kind of update rule. So our update rule is kind of like the way we had an update rule for the weights in the Hebbian learning. So our update rule, there's all different kinds of update rules we could use, but this is the one I always use. It's a very simple one. It's just a binary output. It can either only be +1 or -1. So the output is basically equal to +1 if the sum over all the inputs of an input times a weight. So just take all the inputs, multiply them by their weights, add it all up. If that's bigger than 0, then +1. So let's move this over a little bit so you can see it's different. So 1, and then -1, if that same sum is just less than or equal to 0. So when I ever ask questions on the exam to work simple examples, I always give you the update rule so that you know which one. There's all different kinds of update rules you can use, but this is a simple one. So that just says if when you take each input, multiply it by its weight, if the sum is above 0, turn the unit on. If the sum is below 0, turn the unit off to -0, to -1. So let's just take a simple example of a network like that. And so we always draw the units as thermometers. So here's our 3 thermometer network. So here's 3 units. And we're allowing everybody to be connected. So here's a unit. So here what we'll call the units like A, B, C, A, B, C. So unit A goes and connects to, we're all on the board, connects there's 3 possible connections. It could possibly connect to itself. We'll allow that for now. And then unit B connects to all 3, and then unit C connects to all 3. So we got 9 possible connections. So each one of those are the weights. And so now you can sort of see what the problem is. So the problem is we start off the network in some particular state. So say we started off in the state of 1, 1, 1. Okay, so all the units are on. Say all they're in the previous state, all the inputs and times their weights turned out to be above 0. So now let's update the unit. So let's take so there's different ways you could update. You could update everybody but not propagate all the changes that might have occurred. Or you could just randomly grab somebody and update them, and then randomly grab somebody else and update them. We'll just do it that way. That's easier to think of. So let's just randomly grab this guy and update him. So now we have to so I need a minus. Oh, sorry. For my example, I'm going to put a -1 there. Okay, so say that guy is so say our current state is 1, -1, 1. So that would be, it's a 3-dimensional state space. State space has 2 dimensions, so it's a cube. It's somewhere in a cube, somewhere on the surface of a cube. And so now let's update this guy. And so now this guy is going to have some weights. And the weights could be, let's just say the weights are 2, 4, and 3. Okay, so those are the weights for that guy. And so now we're going to look at this guy's inputs. And so its inputs are it's getting a -1 from itself, and it's getting a 1 from the other 2 guys. And so now we have to run this equation, and this equation says 3 times 1 plus 4 times -1 is -1. Plus 2 times 1 is +1. And so we're above 0. So then we make our output 1. And so what that does is that says that this guy on the next time step is going to be 1. So now we can say, was that a stable state? And the answer is no, because this guy changed. But then we could ask, now that we've done that update, is that a stable state? So all it takes is one guy to change and it's not a stable state. If it is a stable state, you have to check all the units and just make sure none of them change. And then you're in one of these stable states. So I always ask the question, is the network in a stable state? And in that case, you've got to update all the units, and if none of them change, then you're in a stable state. If any one changes, then you're not in a stable state. So now you can sort of see the general picture. So you have all different kinds of weight patterns possible, all different kinds of activation patterns, state space. And these weights are just fixed. So we're just leaving the weights fixed. There's no change in the weights. So as a result of doing simulations and math on these things, what people found out is it's extremely easy to get stable states. In fact, that's kind of the generic thing that happens. If you just take a bunch of units and hook them all up to each other, on average, you're going to get stable states. You're just going to get these attractors where if you start the network off, it'll go to some place and stop. And so that's actually a very common thing. And we'll show an example at the end of a much more complicated model that turns out to be an attractor model, a simple model of reading. So you can see top-down activations and how that turns out to be an attractor model with stable states. Okay, so now when people have tried to analyze these things, one of the things they did was they came up with this idea of calculating something called the energy. So a lot of times physicists they use energy, like you probably heard of potential energy or kinetic energy. It's a single number. It's not a vector, it's just a number, and that number says something about a state of affairs of a complicated thing. So that's what we're doing here. So we're defining an energy, so-called energy, and this energy is basically something that is a sum across all weights. So here we've got, so what does that mean? When you see two summations, that just means you've got a matrix of weights. You can sort of see this thing is like a matrix here, a matrix of weights. And, what does this mean? This just means for every weight. For every weight. So all the possible combinations of rows and columns. So for every weight. So what do we do for every weight? A very simple thing. We just take the input coming into that weight times the weight times the output of that unit. And then we take the negative of it. Okay, so how do we calculate that? Well, we do something like we take let's calculate the energy before we started. So it would be -1. It would be the input to this weight, which is -1 before I changed it, because after I updated it, I would have to change that to 1 for the next time. But before I updated it, it was -1. Okay, so we take the input, that's this guy, times the weight is 4, times the output, which is -1. And then do the same thing for all the other weights. Add up the whole mess. So that's the energy. So what does that mean? So why are we bothering to sort of calculate something like that? So let's look at some simple cases of calculating the energy. So what's a high energy state? So we'll take a very simple case. Say, so let's say we've got two different cases. So here's a unit, and here's inputs coming into that unit. And so say these inputs are, say the unit is -1. Say the weights, just for simplification, the weights are all 1. I'll do it in a different color. So the output of the unit is -1. The weights are all 1. And say the input is all 1, just so we don't have to do complicated multiplication. So if we use the update rule, we can see that this is the next time this is going to change to 1, because the input times the weight are all positive. But if we do this energy calculation, let's just do the energy calculation with just those 3 weights. So if we do the energy calculation with those 3 weights, we have input times weight times output. So 1 times 1 times -1 plus 1 times 1 times -1 plus 1 times 1 times -1. So that's -3. So that's -3 for this thing. And then we take the negative of it, we get 3. So energy equals 3. Now, let's say we update the unit. And so if we update the unit, well, what's going to happen? Well, all those inputs are trying to turn it on, and it was off. And so here's the same inputs. So if we update it, after we updated it, this guy's going to be 1. And so if we run this calculation, it's 1 times 1 times 1. So it's basically 3 for this. Take the negative of it, and we get energy equals -3. So basically, what is the energy? The energy is it's some measure of how happy is the network. So here the network is not happy because all these guys are trying to turn this unit on and it was off. So that's a high energy state. Now here's a lower energy state. All the units were trying to turn it on and it was on. And so that's a low energy. And you could have other, conditions, like for instance, you might have something like condition like this. You could have a condition where, everybody's trying to turn the unit on. 1, 1, 1, 1, 1, 1, 1, 1, versus a situation like this, where everybody, say you got 5 guys, and some are trying to turn it off, other ones are trying to turn it on. You got some mix. Say the weights were all 1 again. If you do a calculation like this, where the inputs are kind of conflicting with each other, the energy is going to be bigger. So this is, energy big, energy small. So this is kind of a frustrated network because the different guys are trying to push it in different directions. So what is the use of the energy? Well, the energy, it turns out, you can see in this case, whenever you update the unit, you reduce the energy. We just saw the calculation here. We updated the unit, and the energy got less, and that's generally true. But you might kind of wonder, but what about all the other weights? Because the energy is not just calculated across you, it's calculated across everybody else. And so we've got to consider all the other weights. So what the physicists did is they said, why don't we just assume that to make our life simpler, we just assume that when a unit goes out and connects to some other unit, the connection coming back is the same. So what is that? That's like a symmetric matrix. So that says if this unit, let's take this input, if unit A goes to unit B, so A to B, the weight equals 2, then just make B to A weight equals 2. So what's B to A? So here's B going to A. So make this guy 2 also. So if we do that, and make this guy the same as that one, and you recognize that as a symmetric matrix. This guy is the same as that one. If you work through the energy equation, you'll see that the terms in the energy equation will be exactly the same as the input weights. So basically what will happen is this will cause the input. So what we said was that whenever you update a unit, the energy that you calculate from the input weights is always going to be less or the same. It can never go up. It's just less or the same. But then the problem is, what about the output weights of this guy? We don't know about what that does, because that could change the energy for these two guys. And so here's the output weights. So here's the input weights. Let me just write it out more. So an update will cause, so here, update causes energy of input weights to go down or same. Could be the same, because if you're in a stable state, it won't change. So that's the input weights. But if we make it symmetric, then update. So, if symmetric, effect on energy same as effect on energy of output weights. Effect on energy of output weights. Same. It's the same as this guy. So that's the, and what are the output weights? That's these guys. Because the idea is that we know that when we update the unit, it's always going to reduce the energy for the weights that are on the unit, but when we update the unit, it's going to change the output, and that's going to go and affect other parts of the network. So when you first hear this, you might think, those physicists, why are they cheating like this? Because it's sort of, we know that the weights aren't always symmetric. But it turns out there's a lot of cases where they are. And it turns out that if you just have anything, say like you have a pyramidal neuron and another pyramidal neuron, and this guy goes out and synapses on this guy, and this guy comes out, synapses back. There's an example that's pretty symmetric. They both excite each other. It's a very common thing to happen. So it's not as crazy as you think. And it turns out even if you just get the sign of the weights the same, that's good enough to get stable states. Okay, so this, and so why do you bother with the energy? Well, you can sort of think of the way the networks are working, kind of this picture here. We'll just draw it out in 1D. You can sort of think of this is the energy going that way, and then these are different states. So, different places in this network. And the way you can think of this network is you have a little landscape of energies as you change the states. And what is an attractor? Well, this is an attractor. And so why is that an attractor? Because you start off at an unstable state and you'll sort of go downhill. You're always, whenever you update, you're always reducing energy until you get to the point where you stay the same. And that guy is an attractor. And we can sort of define it by just saying that's a low energy point. Now there might be some other lower energy point over here, like that we can't get to. You only could get to that one by just, starting somewhere over that hill, and then you would get to this other attractor, another attractor. Okay, so now this sort of seems impossibly abstract. So let's just take a real example. So that was just 3 units. Just take a real example of a model that's kind of related to something that sort of seems somewhat psychological. So this was a model that was done by Rummelhart and McClellan many years ago, trying to look at a reading model. So it's a very simple model, and a lot of people had the idea that there's different levels in the model. So you have different levels of features, letters, and words. And so how did they make this model? So they started off with some letter features. So here's the possible features, and it was a very simplified model that only had 4 letter words. So here's all our letter features, and when you look at these letter features, it just makes, I'm old, so it makes me think of the way the numbers on gas pumps used to look like, probably about 1985 or something like that. So how could you represent a letter with this? Well, if you turn on these segments like this, and that one, and that one, and that one, and that one, then we have an R. So there's an R. Now we have another higher level of the network, and the higher level of the network is the letter. So this is the letter feature, And now this is like the actual sort of letter part of the network. So this is letter feature. Let me erase this guy. And now we're at the letter level. So how would you wire this network up? You would wire it up. Here's a whole bunch of letter units up here. And one of them is an R. So here's the R letter unit. And so you're going to wire up these guys all to the R. And they would obviously hook up to many other things because, you know, they're going to hook up to the B and stuff like that. So we wire all those guys up there. So there's a lot of connections in this network. So there's also going to be a B, and so like this thing is also going to go up to the B. Okay, so that's our letter level. So these are letters. And then finally we have words up here. So so the words. So now we have a whole bunch of words up here. And this is just one big guy like that. Okay, so that's got a whole bunch of word units up there. There's thousands of connections, 1 million connections in this network. So what's, you know, an example of a word up there? Well, we might have rate. So here's the word rate. This guy. And so what is rate is going to get an input from the R. And of course it will get input. There'll be an input from A over here. So here's the A unit. At the second position, this guy's gonna go up there. So I'm only drawing a few connections, and R is obviously going to go to other words like root. So you have another word, you know, root. So I'm only drawing like a tiny number of the connections. So that's the first letter up there. Okay, so now the whole idea of this was to try to make a model of top-down processing. So the idea was that, and what was this based on? It's partly based on data from having people read words. So if you read it, it turns out you can actually read, you can say whether or not there's an R there better if you're presented with a word like rate than a bare R. So amazingly, if you just pop up a bare R and say yes or no, is there an R, versus pop up rate, yes or no, is there an R, it's actually faster this way. You can actually do it faster when you have the word. And so what that implies is there must be some connections that come out of this guy that go down to essentially the letters that word contains. And so the idea is if you see rate, some of the other information about the A and the T and the E is activating the rate unit, and then the rate unit is going down and activating the R down there, and then making it a little easier to recognize an R, especially if there's something blocking a part of the R. So that's a real phenomenon. You can actually you can say whether or not there's a letter in a word faster if you see a whole word than if you just get a bare letter. So I haven't drawn any of those in. There'll be like 1 million connections coming down to all to essentially every. So there'll be a connection here. This guy's going to go down and make a connection to the A second position there, so that guy will get some feedback. But then they also noticed these guys should compete with each other, and so this guy should basically inhibit all his friends. So, you know, if rate is activated, it should slightly inhibit root, because the idea is that we want to sort of, if we get some evidence for rate, we want to suppress some of the other guys, and then they won't have any feedback connections. You can see quite a complicated network there. So, and then they said, well, the same thing should happen for the letters. And so if you see some evidence for a B in the first position, you should inhibit the other letters. And everybody else should do that. So R should inhibit everybody else, B should inhibit everybody else, rate should inhibit everybody else. Same thing over here. So it's quite a complicated network, and if you run this network, it can do a good job of reproducing psychological data for being able to recognize a word faster if it's in the context of an actual word. But it turns out that effect of being able to recognize a word faster in the context of a word works for non-words as long as the non-words sort of look like a word. So if you get a non-word, I think wrote is probably a non-word. Learn by rote, is that W? I can't remember. Neep, that's a non-word. So if you get a word like that, there's a lot of other words that are like that. It's not too bad of a word. It sort of looks like a word. It's like, X, R, T, Z doesn't look like a word. But it turns out that if you take a word like rate and you take a completely illegal non-word like something like that, so that's a non-word. So most psychologists would have said, well, that one's not going to help us out because it's really it's a violation of a non-word. This one's a pretty good word. This one's just like, this one doesn't count. Turns out if you do a test with this, this helps. So this helps you recognize an R, even though it's not an actual legal non-word. And if you do that with the model, it predicts this. And why does it predict it? Well, it's really close to rate, and so most of the network is going to work even though there's a bad X there, and that's going to give you a little extra feedback, and that's going to make it easier to recognize an R. So you can see we're sort of getting at some psychological phenomena. But what is this thing? Well, it's just an attractor network. So when you run it, what happens? You get attractors. And what are the attractors? Well, the attractors are basically a recognized letter. So if we run this network and just plot out basically all our word units. So this is activation. And this was an attractor network where the units, they weren't just -1 and 1, they could be like 0.9 or something like that. So the units they weren't just binary units. But if you look at what happened, if you start off the network, basically all the words, you can sort of start them off at a very low level of activation. And then you apply say rate to these units down here. Then what happens? Well, the unit goes kind of, all different units come up and go down. So there's there's 1,000 units up here, so because they did lots of words. So you get like a whole pile of them going up and down, and then one of them will go up and stay up. And then if you keep running the units, what happens is these guys all stop changing. And so so say this one is root, and this one is rate. The rate unit, rate word unit. So what's happened? Well, now we've reached a stable state. So this thing right here, the network is in a stable state. It's in an attractor. So why is this a attractor network? Well, look at the weights. They're symmetric. So even though this complicated thing, you got letter features, letters, words, inhibition across things, it's all symmetric. And just think about it. If everybody inhibits everybody else, that's symmetric. So in other words, like B inhibits R, R inhibits B. That's symmetric. What about the top-down activation? Well, if R excites the rate unit, and then rate comes back and excites the R, that's symmetric. What if root inhibits rate? Well, rate is going to inhibit root. It's all symmetric. So this is a classic attractor network. This entire model is just a really big attractor network, even though it kind of looks like it's got layers and everything. And it behaves like an attractor network. You start it off, you give it an input, it does a whole bunch of stuff, and then it just settles on one and stops changing. All these units stay the same. So as soon as you get past that point, you're in a stable state. So that shows that you can actually apply this very simple sort of physical idea about energy and updates and attractors to much more complicated models that have different levels of organization in them. They're talking about psychological concepts like words, different kinds of non-words. So let's just talk about one more thing at the end, and that is if we go back to our simple network, just to sort of, so we just had three units in our simple network. This unit had 10,000 units in it. Kind of hard to draw a picture of that. So we just go back to 3. 3 is the maximum that we can. So here's the XYZ axis of this simple 3 thermometer network. So what are the possible states? So if this is 0, 0, 0, that's not a possible state because because our state was only -1 and 1. So this is the state space. This is the state space, kind of like the 2-dimensional one that we drew, but with 3 dimensions. So that here's our state space. But what are the possible states? Well, the possible states are basically just the corners of the cube. So say this corner of the cube is all the units on. And then this corner of the cube is, say, the y unit off. So that would be 1, -1, 1. And so what are all the states? Well, the states are basically just the corners of the cube. Because that's the only place, in our binary network, that's the only places you can be. You can just go on the corner of the cube. So there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 possible states. And what do our stable states look like? Well, let's say this guy is a stable state. We'll just say this guy's stable. So that's an attractor. So what that means is that if we start off at this guy, so that guy is going to be, say, -1, 1, 1. So if you start off at that guy, it's not stable. And when we update it, it jumps to the stable state. And if we start off at this guy, it goes there. If we start off at this guy, it goes there. So that's one of our attractors. And then say there's another attractor back here. So that guy is a stable state also. And say that, so that guy is, -1, -1, -1. And so that guy, if you start off at this one, you'll go there, this guy might go there, and this guy might go there. So that's what our sort of landscape looks like in our very simplified 3-dimensional network. In this thing, what does this look like? It looks like a nightmare, right? It's got like 10 It's got 10,000 dimensions, and not only that, they can be inside the cube, much harder. So that's why I just start off with this very simple one, because you're just stuck to the corners of the cube. And some of those corners of the cube are stable and other ones are not stable. If they're not stable, when you update them, they eventually get to a stable and then you're stuck in the stable. So that's, even though we started off very simple, this is maybe seems a little more complicated than just thinking of like an attractor in a 2D space, where you aim for that attractor like that kind of analog attractors. But it's the same thing is going on. This guy's a stable state. Nearby ones will get to it. This guy's another stable state. Nearby ones to that one get to it. Okay, I think we'll end the recording there and take some questions.